So yeah, my name is Rynge. I'm at UC. I'm here talking about Access Pegasus, and which is a hosted workflow system under Access program. And there's a lot of tie-ins here, so don't be worried. You are in the right session here. And part of this, I'm also going to talk about bringing your own capacity. This is a Miron term for using allocations with Condor, right? So the idea here is that the OSPool, for example, is something that's a shared capacity. You come in and you can use, it's just there for you. But what if you have an allocation on one of the access systems or a DOE system? How do you utilize that allocation for your workflow jobs or your Condor jobs? So there's a little bit of a journey to get to the access. Am I really loud? It just echoes a lot. Oh, good. Okay. There's a little bit of journey to get to the access part of this. So I'm going to start just talking about Pegasus a little bit in general. So Pegasus, it's a scientific workflow engine, and there are many different kind of definitions of what the scientific workflow is. We are using the kind of traditional one and what you've seen here in the morning with DAGmen. So our workflows are all DAGs, where the nodes are tasks, the edges are dependencies. Sometimes we represent this by even using the, we put the data in the DAG itself just to kind of show that the data is something that's really important to Pegasus and something that we manage in these workflows. Pegasus has been around for a long time, not as long as Condor, but we are over 20 years old. Different names, different kind of funding sources and things like that. But what I want to point out that even though I'm talking about this in the access context, with my slides here and everything, Pegasus is also a standalone open source product. So you can always download it. It's pretty much installed on every of the OSG access points. So it's not access specific. What is specific is the kind of the host environment I'm going to talk about here later. The other thing I want to point out with this slide is that Pegasus builds on top of Condor. We are, standing on the shoulders of giants. So we are building on top of DAGmen. We're building on top of all of Condor, but the SCID. So the SCID and the DAGmens are, integral parts to the Pegasus success. I'm going to talk a little bit about success stories later. But some of the parts that kind of sets us apart, right, is data management. Like, think about what we heard today earlier from Cole about how he talks a lot about the jobs, and obviously there are dependencies, but there's really no data management in there. That's something that Pegasus adds on top. Like, we are very, very focused on data, and you will see that on a lot of my slides is how that comes in. So even though we're running DAGs, we are going to also talk about how data fits into that model. All right, so the key concepts here, the main thing to keep in mind when you use Pegasus is that it is a workflow planner. That means we're starting with a higher level workflow description, and then we plan it down into executable version of that higher level description. And the executable workflow here, like the executable part, is a DAGman. It's a very, very advanced DAGman with a lot of stuff in there, but it is a DAGman. The higher level workflow language that we have is something that we have developed ourselves and is kind of unique to Pegasus. Some people call this, like I call it the planner, but there's also the concept of being a compiler. And the reason why we like to kind of compare to compiler is that just like a compiler optimizes your high level code into something machine readable, and when it's doing that transform, it does all the.
We're not sharing on Zoom.
So. Oh, that's right. All right, I'll keep talking. What was I? Yeah, so it's a compiler, and so the compiler optimizes your code as well. It can unroll loops and things like that. The same thing happens with Pegasus.
Did you share?
Right? We go from this high-level language to the executable one, and it's really DAG transforms. Right? So we can take a graph and we can do performance improvements. We can do data placement. We can do data management, and part of that is part of the optimizations I'm talking about. There's some stuff. Perfect. Yep. Thanks. All right, so here's an example of that going from the high level to the executable workflow. So on the left, we have a workflow. We call this an abstract workflow. And the reason for being abstract, well, is that it's not execution environment specific. There's no paths in there. There's no specific software or anything like that. It's all kind of high level. And so an example of that is the file name we call a logical file name. So we know that we need this piece of data. There's a handle to that data, but where that lives and where we're getting it from, that's not resolved yet. This workflow can be shared, right? We can publish this, we can give it to our collaborators, and they can plan it on their site. And the abstract workflow also allows us to move these workflows around. So we can plan it for different environments, different systems at different times. The arrow here indicates a planning step, and on the right, we get this, the executable workflow, the DAG. And you can see in this example, we have added a few nodes. So up on top, we have some data staging. That's part of the data management, obviously. We need some data for this workflow. So Pegasus has decided where to get the data from, where to put it, and that's a node in the graph now. We see the rest of the structure there. We see there's some cleanup jobs added. There's some data staged out at the end and some data registration jobs. The data cleanup jobs is an interesting example of the fact that we're planning this whole workflow before executing. Before we're planning this, so we know exactly where we're placing this workflow and what is coming and when it's coming. So by doing so, we know when data is needed and when it's not needed anymore. So we can go up in the workflow and say, if this data is not needed further down in the workflow, we can add cleanup jobs, and we can then minimize the kind of data footprint. So there's a lot of those kind of graph transforms or graph optimizations that happens in that planning step. The other thing that's important to understand here is that this mapping, what the right-hand side looks here, it's not the same all the time, right? That depends on the execution environment that we're planning for currently. So this is probably maybe a shared file system because we only have a couple of staging and stage up jobs. If we ran on, let's say, Amazon, this would be structurally the same, but maybe we would use S3 URLs, and we would have a different kind of data jobs in there to make sure that we can run in that environment. The way that we create these workflows is via an API. And so there's a Pegasus API that allows us to add jobs, add dependencies, and add pieces of data into it. And that API then spits out the YAML, which is the actual workflow. The reason we use an API here is that it's really scalability, right? So we have obviously tried, over the 20 years I was telling you about, we have had explored using graphical user interfaces in different ways. And there's really nothing that scales, compared to this API approach. So, have hundreds of thousands of jobs. You're not going to kind of edit that in any kind of graphical interface. There are ways of visualizing your workflow afterwards. Like we can obviously create the graph and stuff like that, but we're not editing it graphically. It turns out that this approach fits very well into many of our users' methods of working, right? So like they have steps in when they generate these workflows, right? They have, for example, a data find step where they say, okay, I'm going to query my database. So I'm going to look at the files on my file system to know what I'm going to compute on. So there's like a natural for loop there. And you just, for each object in that data set, create a job. It's very, very natural once you start seeing this happening. Okay, we have a Python API, we have a Java API. We did have an RRR API, but really nobody used it, so that's getting deprecated. Python is where it is. Like, I mean, that's pretty much all of our users is using Python now. So I said the abstract workflow doesn't have any specifics. So how do we kind of fill in those? Like, how do we decide where to place data on a site, for example? And so when you plan, you need that abstract workflow, and you also need these 3 catalogs. And this is what describes, so for example, we have a site catalog that describes the execution environment, the compute site. If that's a Condor pool, that's very easy, right? You're saying I have a Condor pool, and if I'm doing those kind of data transfers, there's really nothing else to describe. If you are running against an HPC center, they have a specific place where they want you to do your data I/O on, and so that's a file system that's probably described in the site catalog. You could have things like endpoints, like data endpoints in there. Like if there's a specific way of transferring data into a site, that also goes in the site catalog. The transformation catalog, transformation really, this is a different name for software. So software that's needed by the workflow that could be pre-installed on a site. It can be something like a static executable that we can transfer around, or more and more, obviously, containers, right? So you're saying here's a container that you can use to fulfill the requirements of the jobs in the workflow. And then we have the replica catalog. And the replica catalog is, think about this as a list of input files, right? So this is where can we find copies of those input files that we need. And it doesn't have to be a single file, right? So we could have one of these logical files that I have here on the previous slide. Right, so we're talking about this logical file name here. And then we can have multiple copies of that floating around out there. Like, for example, you could maybe already have a local copy of that file, or it could be in 2 different, it could be on, let's say, extreme case, there's one copy on Google Storage and one on S3. And you can tell Pegasus that they both exist, and then Pegasus can make the decision at runtime, which one should it bring down at any given time. Most of the time, though, for simple use cases, you have a one-to-one mapping. There's a logical file that exists in one place and one place only, but you could have multiple ones if you want to. I've mentioned a couple of times about transforms to the graph. Here's one example of the kind of transforms that we do. This is task clustering, and the reason for task clustering, there are 2 major ones. One is I have really short tasks, and combining them together into bigger jobs, I can run them more efficient. I can actually schedule them more efficient, right? So the scheduling overhead per task is just lower because I schedule them as a group. The other reason for task clustering could be data reuse. So I have these tasks have the same kind of inputs. So by grouping them together, I can just stage the data once, and then be more efficient about the number of downloads of input data I have to do. We do clustering like this, like the horizontal, which is per level in the workflow. You can also do it vertical, which is really useful in, for example, bioinformatics or cryo-EM or something like that, where you have kind of strands of jobs in the workflow, and you can group them by those strands and then kind of think those as a big job instead. And you can also label-based the clustering, so you can basically color this graph differently and then create clusters like that. That's a little bit more unusual, but it is available. Another example of how we do transforms on the workflow on graph is data reuse. So in this case, we have this workflow on the left, and during the planning step, when the planner using the replicate catalog, it can notice that there are files, partial data already available in there. So this partial data could have come from something like an overlapping workflow or a previous run that was that for some reason you stopped or something like that. But we have partial results, and Pegasus notices that and says, if we have these data pieces, there's no reason to rerun these jobs, and it prunes them out of the workflow. This is a very clean example. Sometimes it doesn't get as clean, right? Because let's say that you have, let me see a good example. Like there could be multiple, right? For this job here, it needs data from this job and from this job. And if you only have data from one job and not the other one, we still can't remove that job. We still have to redo that computation. So, it's a clean example, but sometimes it's not as clean because of other data dependencies that you might have in there. Okay, an internal tool that you don't really see unless you kind of dig down into how Pegasus does things is Pegasus Transfer. And the reason I want to talk about that here is I've said multiple times, data is dear to our heart. But the reason I have Pegasus Transfer here is that in some cases we use Condor transfers, right? We can get away with a lot of stuff by just using the transfer input and transfer output files and stuff like that. But for the more advanced cases, we use Pegasus Transfer. And it gives us things like parallel transfers. And this is a really neat thing, for example, when it comes to, don't go to download a lot of stuff from HTTP or something like that. Protocols that are not parallel in nature, we can do parallel transfers, parallel connections. So, it's a very efficient way of doing that. Automatic retries. Another neat thing here is the two-stage transfers. This is not optimized for performance, but for kind of usability. So let's say that you have a researcher that has data on SCP, and now they want to go to the cloud, and the target here is S3. So the traditional way of doing that is, hey, the researcher, you have to upload it to the site that you want to go do compute at. But because Pegasus is data aware, we can just we can point Pegasus and say, grab data from this SCP data source, and figure out how to get it to S3, and that's these two-stage transfers. So that means we're downloading it, like if those are two incompatible protocols, we can download it in one step and then upload it in the second step. So again, it's not the most efficient way of doing it, but it is really neat because the researcher doesn't have to worry about how to do these two-step transfers. So another thing that we kind of add on top of this is automatic integrity checking. And this is something that, it actually came out of OSPool work we did many, many years ago when we did a lot of transfers on HTTP. And we noticed that, everything wasn't perfect. There was sometimes we get data that was corrupt. And it's a little bit better today, I'll tell you that, because of the way we're doing transfers, but it's not perfect. Right? So like there could be data that gets corrupted in transit, like between different endpoints, or it could also be at rest, right? Like data sits in a storage somewhere and gets corrupted for some reason. So the idea here is that we do not want to do compute on data that has been corrupted, right? We want to detect this and we want to stop doing compute when it happens. So if we step through this example here, we have a little workflow. There's two tasks, input file, an intermediate file, and an output file. And the first job, it's up here on a compute site. If we look inside this job, like even the job looks like a little bit like a workflow. It has many steps to it. It's just kind of a graphical representation of what's happening because it's all linear. But what happens is that we pull a piece of data in from some input data site. This node here is data integrity. So before we do the compute, we recompute the checksums and we validate them against the known checksums. When the job is done, immediately after, we know what data pieces, because we do the data tracking, we know what data pieces we expect out from that job. and we can calculate checksums right there and then. So we got the data, we calculate the checksum, and then we carry that through for the rest of the workflow. So that data goes into the staging site. When job 2 comes, we pull that data in. So this is, instantaneous almost. We push it, we pull it, and then we do an integrity check again. So make sure that we downloaded the same data that we created in the earlier step. There's something else I show you that I don't show you on this. When we have a piece of output from the workflow, and you tell us to put that in a long-term storage, most of the time we push it, then we pull it back one more time, and we inject the checksum again. This is all transparent. One of the things that happened when we did this work was, we got feedback, and people said, "Hey, this is going to take a lot of time. How much time are you going to spend doing computing? How much versus calculating checksums?" And it turns out it's very, very minor. It's like a couple of % of time maybe. And it scales with the data, because the more data you have, the more compute you're doing. So that's actually like kind of, it stays in step with the amount of data you have. It's not really an impact of your work. You can't turn it off also, obviously. But the red thing here, job failure is triggered. So if we do detect integrity failure, we stop and we're not going to compute. So that's a job failure that we add into the DAG. And talking about these job failures, and there's a couple of different ways of doing this in Pegasus. The out of the box way is obviously exit codes, Unix exit codes, and but we also deal with a lot of older codes that have things like, check the output for this one string, or if you see this string in the output, that means failure. So we can also check for messages like that in the output or the error files. And we use a lot of DAGman here. We use the job retries from DAGman. We use rescue DAGs, right? So this is important, and I think Cole talked about that, is that if we get to a point where we can't make any more progress, we stop the workflow, and you can start it later on from that same point. Right? Like we have exhausted all the retries, now we stop, and we let the user kind of deal with it. So a little bit about success stories, and I'm not going to talk about them as in detail, but I want to kind of talk about them from a point of view of features that have been driven by them in Pegasus and kind of interesting parts of that. So the first example here is the Southern California Earthquake Center. They have a workflow that they've been running for a long time as well, called CyberShake. And this is a massive workflow that always hunt for the best place to kind of run this. So they move around to whatever the newest kind of leadership system in the NSF cyber infrastructure kind of environment is. This slide is a little bit outdated, but they ran it on Titan and Blue Water. So those are, I'm not even sure those machines are around anymore, but they are, last generation maybe. But what's interesting about this workflow is that it's a mix of serial jobs, of parallel jobs, and GPU jobs. And so a major part of this is really how do we kind of transform the graph? How do we group jobs? How do we cluster jobs to make them run on the resources that we're talking about here? So job clustering is a big deal. There are parts of this workflow where we take thousands of jobs, pack them into one job, make that job look like an MPI job, and then hand it off to the resource. And the reason we're doing that is, again, not performance from our point of view. The jobs will run the same way. However, this is basically a requirement from the sites that we're running. They want parallel jobs. They want large, that's not to be parallel, but they want large jobs. And by combining them and creating these MPI clusters, we can make this workload, this high throughput workload, fit the expectation that the site has. It's a little bit of tricking, but it works really, really well. And then obviously, the other thing that's interesting about this is for these bigger runs to work, there's usually more than one site involved. So this part here is on Titan, and this one is on Blue Waters. So again, Pegasus have to think about this and say, okay, if I'm going to run on two sites, there are some data transfers that will have to happen between site A and site B. And this is, we planned this out, right? The Pegasus plans the workflow. So before the execution, so we know where the data is needed, and we can set up the right data transfers in the DAG. Another example, this is a OSG user, Xenon. This is a really good example what I talked about before, how data find and using the Pegasus API to generate the workflow will work together. So they have their data, their metadata sits in MongoDB. So when they generate workflows, they say, hey, for this specific run that we're interested in processing, what's all the data pieces? For all those data pieces, generate the jobs in the workflow, and then submit the workflow. The other thing that we haven't really talked about, but when the workflow runs, it also collects a lot of provenance data. Like it collects, like every time a job runs, it collects information about that environment, about the runtime and performance of the job, and that goes into a little database for that workflow run, and you can pull stuff out. So this example here is high-level information that we pull out, where in this case we can see tasks and jobs. So the tasks here is there's 4,000 tasks and 4,484 jobs. So this is the reason there are more jobs than tasks, right? We added data management and cleanup and things like that. We ended up with more jobs than tasks. You will also see that we did some retrying, but at the end, nothing failed, nothing incomplete. So we ended up, running even more instances of these jobs than we had in the workflow. But at the end of the time, it all worked out in this case, and we got a successful workflow run. We have things like, okay, that took 5 hours to run that workflow, but it was 136 days total compute time. So this is really good stats for a high level. We also provide, details of breakdowns on per transformation and per job and per execution. So you can get, for example, CPU usage, memory usage, and all that stuff from all this. That's all collected by Pegasus. And the last one, this is also an OSG user. The Event Horizon Telescope, and Rob talked about this project yesterday, I think, on Monday. And this is a different workflow from what he was talking about. So it's actually an older one as well. But what I want to point out here is that the model that they are doing, having a data store that sits outside OSG, right? So this is the data sits on something called Cyverse, that's out of the University of Arizona. And they came to us and said, we have our data already in Cyverse. So, do we have to transfer it? And we said, no, we can pick it up directly from Cyverse. We can do the processing in OSG and then ship it back to Cyverse when we were done. Initially, the interface into the Cyverse data store was iRods. So we used iRods. It turns out that wasn't really able to keep up with the amount of processing that we needed to do, and we switched to WebDAV. Right? And this is an example of the planning, having an abstract workflow, how that kind of benefits, right? Because we didn't have to redo the workflow. We didn't really have to go in and edit. All we had to do was change that site catalog from iRods to WebDAV, replan, and the workflow was the same, but the data management was different. Okay, so now we're getting to Access Pegasus, finally. So Access Pegasus, the reason I'm talking about Access in this case, right, is that my team, which is the Pegasus team, is now part of Access support. And this is one of our projects. Obviously, we have other projects as well, but this is an interesting one to look at. And to realize what's going on here, you have to kind of know that when we transition from Exceed to Access, we changed how we do, like how the project was funded. In Exceed, we had a full, like the whole project was funded as one big grant. When we moved into Access, there was 4 or 5 different tracks. So there was a track for access allocations, there's a track for operations, there's one for metrics, and there's one for support. And so when we proposed, what we wanted to do for access support, we had to come up with some innovative ideas on how to change support and how to kind of improve the user experience. And this pyramid here is what was in our proposal. And the idea here is that with access being a little bit smaller, especially in money, we had to be more efficient about supporting users. And one way of doing that is to have easy to use tools. So the idea with this pyramid is that the bottom here is number of people, number of access users. So for the masses, what we want to do is to have easy to use tools that basically, eliminating the need for support. Like you shouldn't have to contact support for everything. You should be able to be self-sufficient. And then if you need support, obviously there are other tiers here, right? Current knowledge base. This is documentation. This is kind of a Q&A system. There's a ticket system, obviously. And then if you need even more support up here, Match, Plus, and Premier, these are attached expertise to your project. It's basically allocatable people that you can get onto your allocation. But so my focus is obviously down here, easy to use tools. And the 2 tools that we provide is Open On Demand and Pegasus. And On Demand is a very, very nice web interface for HPC systems. And there's a little bit of a plug I would like to make here, because Open On Demand is it's very modular, but one thing that's missing here is an HTCondor backend plugin. So if you have interest in that, like I'm trying to kind of rally the team, the troops there a little bit. If you have interest in this, and I already have a few people, let's get together and see what we can do. Because it is generic. It means that you could do job submission via Condor, via On Demand via Condor, and I think it would be a pretty nice thing to be able to do. The really beautiful part of Open On Demand is that it authenticates via CA logon, and then it uses HTTP proxying. So if you want to provide things like Jupyter Notebooks or RStudio or any of those kind of HTTP environments, they're really nice to run them behind Open On Demand, because On Demand does the proxying back into your cluster. So it will start Jupyter Notebook on one of your compute nodes, and then just interface it directly into Open On Demand. And it's just really well done. And the second one is obviously Pegasus. But to make this even more confusing is Access Pegasus is a merge of these 2. So Access Pegasus uses Open On Demand to run workflows. And the reason we're using Open On Demand here is the web interface, the authentication, and we can run Jupyter Notebooks. So the authentication part, anybody with an access allocation can just log in without asking for an account or anything like that. They are automatically enabled on the system. And so this is PegasusAccessCI.org. You go there, you get the CA logon prompt, and CA logon together with the access IDP that you registered in automatically will just mean that you can be logged in automatically and you don't have to worry about it. When you log in, you get this interface. It's a very simple Open On Demand instance. Usually, like the bigger sites that have a lot of different apps here. We have 2. We have Jupyter Notebooks and we have Shell. And the Jupyter Notebooks in this case is what we're going to use to run workflows with. It's not a requirement to use notebooks with Pegasus. You could actually drop to the Shell directly if you wanted to. But it is nice. People like the notebooks. They like that interface. It makes a lot of sense. Going back to what I said about the data find, like you can explore data, you can do the workflow, and then you can keep on kind of exploring the output of that workflow all in the one interface. So it is pretty neat, and we have some extra glue in the Pegasus API to make this even better. And I should also say that, actually, I'll get back to it. We'll get there. Okay, so the other thing that's included in this is easy to use example workflows. So this is a band we want users to be able to self-serve. Like when you log in, you will find that there's already a directory in your home directory there that has the example workflows. It also has a self-guided tutorial. So you can step through these, learn how to use Pegasus directly in the notebooks, and then at the end we can look at these example workflows that maybe fits some needs that you have. The types of workflows we have in the example workflows are some that are AI, there's some machine learning, there's an LLM one, we have some astronomy ones, bioinformatics. So for example, protein folding and things like variant calling. Now, once we have the workflows, right? We have workflows submitted or generated, and now we want to run them somewhere. So we have a few different ways of doing that. Let's get some water. So bringing your own capacity. Why is that important? Well, all the access resources are allocatable. So for us to work in this environment, we have to figure out how to run on these allocatable resources. And what we're seeing on the right here is 4 different types of access allocations you can get, like this different sizes, how much effort it takes to get them. If you have done Tergrid or Exceed, and you said, hey, that process sucked, it was really difficult to get an allocation, it is much better in Access. For you to get started, like the 400 credits here, it's basically a paragraph that you can submit at any time. And it usually usually comes back at in a few days. It is easy to get one of these allocations. Now, if you have a big one, effort goes up, 3-page proposals, 10-page proposals, and those usually goes into a panel, right? So like up here, yeah, it's peer review. Down here, you coming in with a grant or being one of a U.S. institution, it's basically automatic. So what's the motivations? Why do we care so much about bringing your own capacity? And why can't we just use OSPool all the time? Well, I mean, there are some advantages of these allocations. So a lot of it has to do with increased capacity, but also kind of different capacity, right? So maybe GPUs or some of these sites that have really good parallel file systems. So maybe I/O is important to you, and clouds with configurable resources. A common one. So I'm also, my other hat here. I'm doing OSPool facilitation, right? And a very common thing that we run into with OSPool users is runtime. They have long jobs. They say, I've made this job. It runs for a week. There's no way I can break it down and make checkpointing or something like that. And that is not a good fit for OSPool, right? We are OSPool. We're just using other people's machines. We're borrowing machines. We cannot run long jobs like that. So an easy way around that is to go and say, hey, well, but a cloud VM that I can run for as long as I want. And it's still a Condor job. It still fits into high throughput mindset and approach. It's just a longer job. And so there are times when allocations are really, really advantageous in that case. Access Pegasus, and I'm going to show you more details about this, but we do support both shared resources and bring your own capacity. So the way we do that is that jobs in our system, and when I was saying jobs in our system, I mean, it's, most of them comes from workflows. You could run regular Condor jobs. It's not, it's same thing at this level. The jobs in our system, they can go to different resources. And I'm going to explain each one of these a little bit more into detail in the next couple of slides. But the the kind of the paths for those jobs, we can go to a test pool, we can go to cloud resources, you can go to something called HTCondor Annex, or the OSPool. Right? So this is all currently the different paths that the job can take, and we might have even add a few more here. If you don't do anything, if you just run the jobs in here, we're not steering these jobs. Like they will basically go to wherever there's availability. But these different targets work in different ways. So let's start with the test pool. It's a shared capacity because it's available automatically to anybody on the Access Pegasus system. And it's a tiny amount of resources, maybe 100 cores or so, that's always available and that you can use for debugging your workflows, testing simple things. So you can just come in, run the workflow without even, doing any kind of provisioning. It's really, really useful for tutorials, right? We don't have to even have users have allocations at that point. They can just come in and run automatically. In classes, right? Like we don't have to do any extra setup. So it's really, really neat. But it is a limited resource, right? So if your workflow, now you have done your debugging, now you've done your setup, and you want to run bigger, the test pool is not appropriate anymore because it's too small for you. So one of the options is cloud resources. The cloud resource on Access is a machine called Jetstream2, hosted at Indiana University. And the way that we bring in capacity from Jetstream2 is we have a pre-configured virtual machine that you can just start with a few parameters. And those parameters is your username and token, and you have to insert them in this horrible looking YAML here. But you do that once, you copy and paste it, and then you're off to the races. These VMs are set up to self-terminate, so almost like a glide-in, but as long as your workflow is running, as long as you have demand, this VM will stay around. When your workflow is finished, the VM will automatically shut down and not cost you service units. And this is bring your own capacity because the VM that you're doing compute on is running under your allocation, right? So you get an access allocation, you're saying I need 100,000 hours to do this work. I'll spend them on Jetstream by running these VMs. So you will get charged for this user like against your allocation. The second option here is HTCondor Annex. And this is a path contribution. It's part of Condor. You have to have a pretty recent version for this to work well. But the idea here is that Condor is aware of a bunch of different machines and queues. Okay? And these are pre-configured. So when you want to use one of these machines, there's a little command called HTCondor Annex create, where you tell it how many nodes, how much lifetime, what product to charge to. In this case, GPU type, but that's not needed obviously if you don't using GPUs. What the name of the annex is and where to run it. So in this case, the GPU queue on Bridges 2. And this is not a new idea, right? Like we have done glide-ins and we have done, this type of glide-ins for a long time. However, what is new here is that you are starting them by yourself. And by the reason and the fact that you're starting them by yourself, again, you're running under your allocation and you're getting charged for that usage. So, but they are working like normal glide-ins. The glide-in is partitionable, so you grab a whole node, you can run smaller jobs on that. It works really, really well with the high throughput stuff. And yeah, I shouldn't have user on here, but the point here is it's reusable. So the glide-in stays around as long as there are jobs, and it will keep on running jobs. Like you just, you submit one job to the CERM queue at Bridges in this case, and then you can run a large number of Condor jobs. And again, that kind of transformation of workload from a high throughput workload to something that from the Bridges 2 point of view is less throughputy. it's not a parallel job, but they don't see all the single jobs that you might want to use. Another property of the Condor HTCondor Annex guidance is that will only run jobs for user started it. And this is important, right? Because it's your allocation. You don't want to pay for somebody else to run their jobs. But it's different, right? If you think about how we do stuff on the OSPool or when we talk about shared capabilities, those we want to share to as many people as we can. So these two, even though they're still both glide-ins, they are configured differently, right? In the shared capacity mode, we're saying anybody can run. In the bring your own capacity, now they configure to only run your jobs. Okay. And the other thing I want to point out with Condor Annex, so yes, we're using this heavily on Access Pegasus. It is available to anybody. I said it's the newer versions of Condor. But one of the things is that it's still under experimental. So you will not find this documented in the Condor documentation. It is, or maybe, yes? Even better. Don't worry about this then. Go to the Condor documentation. But yes, it's still a little bit, we call it experimental. It's still in, not experimental, maybe. I don't know. Yeah, anyways, it's still in development. And the downside to this, I mean, and the upside to doing this, where we have the pre-configured sites, is that you don't have to configure these. They are already kind of figured out. They've already done this hard work for you. So, you know, for you to run on any of these, you just go in and say, I want to use that. And we know how to configure that glide-in for that particular site. The queue, all that stuff is done. The downside to this is that, you know, we can't really add new sites easily. So if you come in a campus cluster or something like this may or may not be the right approach for that. Right. And then lastly, OSPool, which is, it could be shared or bring your own capacity, because in the OSPool, most of the time we think about this as shared pool. You can also get an access allocation on OSPool. It doesn't really matter. Jobs are run the same way, but it's something that we do support. So the only thing that makes a job kind of eligible for running on the OSPool is that you have to set this project name. You have to say, tell OSG, how do you charge for this, or how do you account for this job? And so it could either be an access allocation ID, or it can be an OSG project name that you have registered with OSG already. So this is really an OSPool access point. We use flocking for that. But it might be slightly different from the other OSPool access points that we've talked about this week, right? So, well, for example, we do not have an OSDF origin on this machine. And that's, again, because the environment that we're targeting is the access environments, and what they have is OSN, so the Open Storage Network. Frank talked about that part, and this is an S3 interface, you know, object store. So there are very similar approaches, but it is you know, different. We might do an OSDF origin, but it comes down to a lot about, like, kind of what's the lowest common denominator we have between the OSPool and the access machines. So my last slide, I'm just going to talk about this another example workflow that we just added. It's an, you know, doesn't really matter. It's an LLM RAG one, which is kind of fun to run. But the reason we added this is that we're running a tutorial at PERC, which is in 2 weeks, using this workflow on this system. And the reason this is interesting is down here, really, is that this is configured to run on any of these machines. So basically, anywhere we can find a GPU on the test pool, on cloud resources, via HTCondor Annex, or the OSPool, this workflow will run. Okay. And so it again comes down to lowest common denominator. Like, how can we run containers, find and via GPUs, you know, across these different sites? And it is doable. You know, you have to obviously be very flexible. So this is all containerized. It doesn't use any specific OSPool feature, for example. And by doing so, we can just run it everywhere. So that's next week. So I'll stop there and I'll take questions.